Hi, in this video we're going to talk about binary analysis and how it is related to memory space and how it is organized. This is a very important tool for anybody that is doing low-level work, mainly in C, C++, or assembly language. It is important if you are doing this work on big operating systems like Linux or Windows, but it is even more important if you are doing bare-bone work on embedded systems where we many times have to control things ourselves, understand them and analyze them. We will conclude this video with a demonstration on Arduino where we can see things that we can do if we have this skill set. So keep watching. Okay, so first of all, let's talk about binaries. When we compile and link our program, what do we get? We get an object file. And how is this object file formatted? One format is called ELF, which stands for Executable and Linkable Format. And the Windows counterpart is PE, which is Portable Executable. But we will focus in this video on ELF, which is the standard in the GNU Linux environment. However, the concepts are going to be similar to PE and possibly any other format that is out there. The ELF format includes an entity called a section. A section is a container of data, and the ELF file itself is a bunch of metadata that describes the data and the data itself. The CPU is not going to execute the ELF directly because the CPU does not care about the metadata, but we will get to that momentarily. Let's start with understanding what the section is, and we'll start to do that by looking at the four most important section types. The first very common section is .text. .text includes the instructions that are going to be executed by the CPU. The second one is .data, and it includes initialized globals. We will see examples shortly. The third one is .read-only data, which is very similar to data, except that it includes globals that are initialized and read-only. And the last one is .bss, that is used for uninitialized globals and is more of a scratch space that is being populated and manipulated during runtime. Okay, let's begin with an example of how a program looks if it has just the .text section. Now you will see that I'm using a specific compiler for the ARM architecture that I've selected for this demonstration, and you have to know that each compiler is going to have minute changes in how things work, but the important thing is that you know the concepts. If you know the concepts, you're going to be able to adapt to specific flavors of how compilers do things. So I'm going to create a super simple program. This is hello.c, and I'm going to say int a equals 3. And now I'm going to compile this, and my compile line is gcc hello.c, and I'm going to say -no stdlib because I do not want to link with the standard library, because that will bring in much more stuff that isn't my code and will ruin my demonstration. So I'm going to use only code that I produce here, and then -o.hello.elf, and you can ignore this warning. It's saying that we are missing a symbol. This symbol usually resides in the standard library that I did not link, and this is why it is missing now, but for this demonstration it's fine. And now I'm going to use a program that is called objdump, and objdump can analyze ELF files, and it will help us see what's in the ELF file that we have just produced. The first thing we're going to do with objdump is to dump the section header table. In order to do that, I'm going to say objdump -age for headers and then hello.elf. And now you can see that we only have two sections. One is the comment section that we can ignore for now. It's like a container for stuff like text and things that describe the ELF itself. And we have our .text section, which is our program. And let's focus on a few of the fields. One is the size. You can see that our program is just 18 hexadecimal bytes. The VMA, which is the virtual memory address, is 400,000 hexadecimal, and that the file offset is 10,000 hexadecimal, and that's the offset inside the ELF file itself. Now I'm going to open the ELF file in a hex editor because it's interesting to see what's in there. But before I do that, I want something to compare to. In order to do that, I'm going to use objdump again, but this time I'll give the argument -D, which will disassemble all the sections in this ELF. Now you can see the disassembly of the text section, which is the instructions that are in there, and also that of the comment section. But be aware that an attempt to disassemble the comment section yields some nonsensical information, because those aren't really instructions. It will look better in a second in the binary editor. So now I'm going to open the binary editor, and this is the binary editor view for the ELF file. And as you can see, at the beginning there is a hexadecimal 7F and then the ASCII equivalent of the word ELF. And if you look at the Wikipedia value for ELF, you will see this magic number. Magic number is at the beginning of the file, and it's some kind of marker that this is an ELF file. So now we are going to jump to the file offset of hexadecimal 10,000. And here's our program, whatever I've highlighted here. And I've put the disassembly of the text section done by objdump, and you can compare and see that this is indeed our program. Right after that, you can see the comment section, which is just a bunch of text describing what toolchain was used to build this ELF file. Now when we go back to the section header display, we can see that indeed the .comment section resides in the ELF right after the location of the .text section. So the .text section has a size of 18 hexadecimal, and the location in the file is 10,000 hexadecimal, and the .comment section is just 18 hexadecimal bytes after that location. So that fits what we saw in the binary editor. So what we have seen now is that ELF is a type of container to the various sections. There is a bunch of metadata in there, but eventually what we're interested in is the binary parts. Those are going to be executed eventually on the CPU. There is other types of metadata in the ELF. We will see some of that in a few moments, but maybe you are asking yourself, if our program is built into this ELF file, but the CPU needs just the binary parts, how are those binary parts going to end up in the proper places in memory for the CPU to execute them? Let's see that in a diagram. So on the left we have the ELF file, and addresses goes from bottom to top, and at offset hexadecimal 10,000 we see the .text section with size of hexadecimal 18, and on the right we see the memory, and we know that eventually this will have to end up here at address hexadecimal 400,000. So on big operating systems like Linux or Windows, somebody is going to take the ELF and eventually it will run on the CPU, and this entity is called the loader, and it will do whatever is necessary in order to take the ELF, take out just the necessary parts, and then have the CPU run that. But in embedded systems, many times we do not want the entire ELF on very limited storage, and we don't want a loader, so we just do everything beforehand and store just the binary on our storage and then run it when the time comes. Let's see how we can take out just the part that we need, just the .text section, and then what we are left with. So the flow on a bare bone embedded systems is going to be to first get the bin from the ELF, and then we can store just that bin. We do not need to store the entire ELF, nor do we want to. And this bin has to somehow get to the right place in memory. By the way, it's very important that it gets to the same place for which it was built, because generally code is position dependent. You can build it as position independent code, but that is more complicated, and I would like not to go into that now. So generally, in order to function properly, your code has to be located where it was intended during the build process. You might be asking yourself, who is going to put the bin in the right place in memory? Now, it depends on the architecture. There are architectures where programs has to be loaded to the right place in memory before they start running. And there are other architectures, for example AVR and PIC, where the CPU is executing directly from flash. In that case, we have to burn our flash with the proper memory layout in advance, and then during runtime they are just right there where they are supposed to be. And we will see that momentarily with an Arduino demonstration. In order to extract just the binary, I'm going to use another program from the toolchain called objdcopy. And the command says objdcopy hello.elf minus capital O binary, which means I want the result as raw binary, as opposed to some other formats. One of them we'll see shortly, which is ihex. And then I say hello.bin because this is the output file. And now if I just dir hello.bin, I can see that this file has the size of 24 bytes, which is exactly hexadecimal 18. If I open this file in a binary editor, I can see just my program, which is right now just code, the .text section. And again, I can do a side-by-side comparison with the objdump minus capital D, and you can see that our text section here is exactly what I have here. Alright, so I said we're going to see the 4 main section types, and so far we have only seen 1. Let's go ahead and see the remaining 3. If you recall, we said that .data is going to contain initialized globals. Let's see that in action. I'm going to add to my main.c an initialized global, int a equals 5. And now I'm going to compile that with my usual build line, and then use objdump minus h in order to see the section headers. And now you can see that we have a new section, which is .data, and its size is exactly 4 bytes, which is the global int that we have added. Now if we use objdump minus capital D, we're going to disassemble all the sections, and you can see that the disassembly of section.data, and you can even see here that it's A, and the content is my 5. And of course, ignore this attempt to look at that 5 as if it's an instruction. .data is not a code section. Since A is a global, it also has a linking symbol. And with objdump, we can also see our symbols. For that, we will use objdump minus T. And you can see here that the symbol A is in address 410,018 hexadecimal, and that it is part of the .data section. Now let's go back to our list of sections, and now we will move A into the .raw data section. In order to do that, we need to make it a read-only. In other words, we need to add the const specifier. Now I'm going to rebuild this, and again see the section headers. And now you can see that .data has disappeared because I no longer have a writable global, and now I have .raw data instead. The symbol specifier now shows that A is part of .raw data. Finally, let's add something that will be placed in .bss. As a reminder, .bss is more of a scratch space that our program is going to populate with variables and later manipulate them, but since there is no initialization data to begin with, we do not need to preload any values before the program starts running, nor do we need to store anything as part of the program binary. In order to do that, I'm going to remove the const, but I'm also going to remove the initializer. Again, I'm going to build and see the section headers. And as you can see now, I have a .bss section. You might be asking yourself why this .bss section has the size of 8. And the reason is that there is a padding issue here. You'll see that disappear if I add an initialized global on top of the non-initialized global. Analyze headers again, and voila, .bss has the size of 4. What happened here is that the program has a default setting of having an 8 bytes aligned end address, And without the data section and the BSS section being with just 4 bytes, the compiler had to pad the BSS section with additional 4 bytes in order to hold this constraint. However, when I added back something into the data section with 4 bytes in it, then the compiler no longer needed to pad the BSS section. Those kind of details are exactly what you're going to see when moving from architecture to architecture, from toolset to toolset. However, the principles are going to stay pretty much the same. Now you might be asking yourself, why do we even need to bother separating those different types of variables of code into different sections? Why can't we just throw them together into one place? So the answer is, each one has special attributes that we need to take advantage of and special constraints that we need to take care of. The .text includes our code, and we want to put the code in pages that have execution permissions. For that reason, we need it separate from other parts of the programs so we can move just it into the proper page. When we look at .data, it's something that is writable, but it's also initialized, meaning that we need to load the initialization data from wherever it is stored on our system into the execution memory. However, we will need to place those variables in a writable location. In contrast to that, things that are meant to be non-writable, we will probably want to place in pages that has no write permissions. This way, if there is a write attempt into those locations, our hardware can help us detect it and prevent it. And finally, .bss is different from the others in that it has not need to be loaded. There is nothing there. It's just a defined space where our program is going to put our non-initialized globals. So for example, when we create what is called an image of our program that includes everything that has to be eventually loaded into execution memory, we can omit the .bss simply because there is nothing to load into it. However, when we craft the memory layout of our program, we will need to take into account the BSS location and size because our program is going to use it for non-initialized variables. Now, just for the sake of it, let's create a program that has all 4 types, and then we'll go and see another nice analytic capability of objdump. So I'll just add the missing part, that is the const variable, and I'll build that and analyze section headers. And now we have all 4 types in our program. Now let's see another very important analytic capability. Using objdump with the flag -S, objdump will disassemble our code sections while intermixing the source code into the resulting assembly. That didn't quite work. The reason is, in order for that to work, we need to include debug information when we build. So I'll go back to my build line and I'm going to add the flag -G. Now I'm going to analyze the sections again. And what do you know? I have new sections here that contain the debug information. Now I'll do -S again. And now you can see the C source code intermixed into the respective assembly code. It is important to understand that the debug sections are not part of the runtime binary. When we store the program binary, we will not store them. They are needed only for debug purposes. Specifically on embedded systems, they will not even reside on the system itself. Another important analytical capability is seeing what is the binary product of our program. Let's see a simple example on the Atmel Studio with the AVR microcontroller, toolchain, and simulator. This tiny program calls foo to assign 3 to A, and then it calls bar to assign 4 to A. I'm going to put a breakpoint here and run the program. And then I'm going to attempt to put a breakpoint inside foo, and it fails. Let's disassemble the code sections of this program. What happened here is that the compiler realized that by calling foo and then bar, we're going to assign the same variable twice, and just kick out the unnecessary call to foo. Once that is done, foo was completely kicked out of the code. As a matter of fact, bar was also kicked out of the code. Don't let the source code intermixing confuse you. If you look at the instructions one after the other, you will see that there is no call to either foo or bar. Instead, the compiler generated code that just assigns A inside main, and that's it. If we now look at the symbols, then foo and bar are nowhere to be found. This becomes even more prominent if I'm compiling the same program with the ARM compiler. Notice that I've suppressed all warnings for clarity and also activated high optimization. Disassembling the code sections, and you can see how simple it gets, and foo and bar are again out of the game. Instead, you can see this super simple code that just assigns 4 into A. So as you can see, binary analysis opens up a wide range of capabilities that can help us a lot in low-level programming. It can show us the very final product of our program, whatever is going to run on the CPU. It can show us how the memory layout was intended to be. It can show us the linking symbols and more. Finally, we're going to go to a small demonstration on our friend here, Arduino, and at the heart of the Arduino is an AVR microcontroller. Usually when doing Arduino projects, we will use the serial cable over a USB in order to burn the onboard flash of the AVR with our program. Let's say a few words about what a bootloader is, because our demonstration is going to be something that is similar to a bootloader. When you create a program in Arduino Studio and you hit the upload button, you will see a little LED dance on the Arduino board. This is because there is a small program called the bootloader that is burnt on the Arduino and is talking to your Arduino Studio over serial. The burning flow is as follows. On the left we have our development machine, and on the right we have the Arduino with a pre-burnt bootloader on it. On our development machine, we first build an L file from our code and then extract a bin from it. After that, the studio will use software to do a two-way communication with the bootloader on the Arduino and send our program to the bootloader. This is done over the serial cable. Then the bootloader will burn our program on the flash and jump to execute it. Before we describe how the bootloader burns the flash, let's say a few words about the memory architecture of the AVR. The AVR is based on what is called the Harvard architecture, in which there are separate paths for instructions and data, which means that they are stored into different memories and memory spaces. In the AVR, it is implemented by the flash being the instruction memory and the SRAM being the data memory, except that the AVR also has a small chunk of EEPROM, which is another kind of non-volatile memory. So by saying that the flash stores the program and is the instruction memory, it means that programs reside on the flash and that the CPU fetches and executes instructions directly from flash. This means that we will not have to do instruction loading into some kind of volatile memory, like for example in Intel architecture or others. Here, once you have burned the flash with your program, when AVR gets out of reset, it will immediately start executing from address 0 of the flash. And in this diagram, the lower addresses are at the bottom. There is another small secret memory on the AVR that is dedicated for the task of flash manipulation, and that is the flash page buffer. Its size on the AVR that is in the Arduino, which is model 328P, is 64 words or 128 bytes. In order to burn the flash, the bootloader will first fill the flash page buffer word by word using the special SPM instruction. It will do it in buffer filling mode. Then the SPM instruction will be used again in flash writing mode in order to flush this buffer into flash. This entire procedure will happen in a loop until the entire binary is burned, while dividing this binary into chunks of 128 bytes. Okay, let's look at the code that is doing that. And don't be too worried if you don't get every detail here. It's not what important. What is important is that we will see later the small memory layout crafting that I have to do. But for now, let's just give a sneak peek at the code. So we have our main function where I disable interrupts just in case, and then I call the function write to flash, and then just do an infinite loop. So most of what we have is just the write to flash function. If we look at the function, you can see that first I assigned the Z register with 0. The Z register is going to function as a pointer inside the flash page buffer. Then in a loop, I'm going to assign the value of I into R0 and the increment I, and then again assign it to R1 and then increment I again. This is because the couple R0, R1 are going to form our word that we are going to write into the buffer on every iteration. It works on words. And forgive my inline assembly, I focused on simplicity rather than using the best practice. Now in the loop, after assigning R0 and R1, we are going to use the SPM instruction in order to write to the buffer, and then we are going to increment the Z register in order to point to the next word in the buffer. We're doing this in a loop, and then eventually we are writing to flash, again using the SPM in write flash mode. And notice that at the beginning of the write to flash block, we're setting the Z register again. This time the SPM instruction in write flash mode will use the Z register as a pointer in the flash itself. So in Z low we put 0, in Z high we put 3. Together it will form hexadecimal 300. Once done, we're going to go back to our main function. Now let's build our program and now analyze the section headers, because momentarily we're going to do something a little different and we would like to compare what we have. So you can see that my entire code went into the .text section at the address 0. Now let me give you a heads up. This program is not going to work. The reason is the AVR has a protection mechanism not allowing just any program to write into Flash. In order for code to be allowed to write into Flash, it has to reside in a special location on the Flash called the Bootloader section. Don't confuse that section with the term of L section that we have been discussing throughout the video. So let's see how we can make this work. With the bootloader memory location restriction in mind, our code will look more like this. Whatever we have in address 0 and a little bit beyond will need to jump to the bootloader that is located in the allowed location and then continue executing from there. Our flow is going to be now first jump to the bootloader, then loop over filling the buffer with SPM and then writing the buffer to Flash with SPM, and then return to normal code. In our code, our bootloader for the poor is the function write to Flash. I need to locate this function in the bootloader section of the Flash. On the AVR 328p, the bootloader section begins at flash address hexadecimal 3F00. However, that is a word address, while GCC likes to work with byte address, so we have to double that and use the address 7E00. So that's where I'm going to locate the bootloader, and I'm going to do that by first assigning this function to a new section. Then I will be able to instruct the linker to locate this function at the address of my desire. Practically, I'm going to add an attribute to the function like that. This directive will put the function in the logical container, which is the bootloader section. Now let's build our program again, and notice that I'm instructing to put the .bootloader section at address hexadecimal 7E00. Let's analyze again. And as you can see, there is a new section. You can see in the attributes that this is a code section. And that section is .bootloader at address 7E00. And now you can also see that most of the code is located in that section indicated by the size. And now the .text section, which now contains only our main function, is tiny. It's just hexadecimal E bytes, or decimal 14 bytes. Now comes the moment of truth. We're going to burn the AVR with this ISP, which stands for In-System Programmer, connected at the designated port. Here's how things would have looked like if we have extracted a pure binary from our ELF. So first we would use obj-copy to extract just the runtime binary, and we would craft it to look exactly like the image that we would like to burn on flash one-to-one. And then we would have used the ISP in order to burn this exact image on the flash. However, our burning program does not like to be fed with binaries. Instead, it wants to be fed with IHEX files. IHEX is a standard that describes binaries with text. What we will actually be doing is to extract an IHEX file from the ELF. And by the way, you can do that with obj-copy specifying -O IHEX instead of -O binary. And then our burning program over the ISP would go and burn only the parts that need change. Because our program is so small, this will take a very brief time. The Atmel AVR Studio produces an IHEX file as part of its build. We'll continue doing things directly from within the studio. Let's start by removing the attribute that we have added and building. Now we will use Extreme Burner AVR to burn that IHEX file. Let's open it. And as you can see, this is what is going to be written on the flash, and this is how small our program is. If we scroll down to our target area at hexadecimal 300, you can see that everything is going to be left as FFs. I'm saying left because the default for flash bits is to be at 1, to be set, and when writing we zero down or clear bits. So having everything as FF means that no burning is going to happen to that area. Okay, let's burn. Burning is really quick because only those areas that require writing are going to be burned, and our program is very small. Now, our program started running immediately after AVR was taken out of reset, meaning right after we have burned. Therefore, when we are now going to read back from flash, we are expecting the target area to include our consequent numbers if things were about to work. Let's read. As you can see, reading is much slower because reading is of the entire flash memory as opposed to writing that is just for the parts that require change. Okay, as you can see, the target area was unchanged on the flash chip. Now let's go back to the studio and restore the section attribute. Now we are going to build, but you may be asking yourself, how am I going to tell the studio where I want this section to be located? And this is done in the project settings under toolchain, the AVR GNU linker, and memory settings. And you can see here that it says .bootloader equals hexadecimal 3F00. Okay, let's build. We will do a reload in our burning program, and then we write again. We can immediately go and read things back. And now the display of the burning program is going to reflect whatever is on the flash memory. And we are looking at what is about to happen at the target area of hexadecimal 300. And what do you know? Thanks to our location of the bootloader, the target area at hexadecimal 300 is now occupied with consequent numbers from 0 to 7F. The reason you are seeing them in reversed order is because the AVR is a little endian microcontroller. Alright, that's it for this video, and thank you for watching. Please don't forget to like and share this video and to subscribe to this channel because there is more stuff like this coming your way. See you.